Right now, ready for your minds to be blown? I thought you might be. So, larger molecules. All right? We could show how things go together using every orbital that these things have. But things only matter with the valence shells. So when you're doing these larger molecules, use only the valence shells for your MO diagram. Okay? So we're only dealing with, in this class, we're only dealing with row 2. So we're dealing with 2s and 2p. Okay? So let's do a MO diagram for N2 Dinitrogen. All right? So on the left side, I'm going to have nitrogen A, and on the right side, I'm going to have nitrogen B. All right? So there's 2 nitrogens in my molecule. So nitrogen A and nitrogen B. So nitrogen A has, at its lowest level, a 2s, and then it has 2p, which has 3 p orbitals, right? The other nitrogen has the same thing, so about the same energy. It's 2s, and it's 2p, and the p has 3 slots, right? So each nitrogen has 5 valence electrons. So we fill our valence shell 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay? So now, we've already sort of dealt with the S part, so with our hydrogen. So the only difference here is that we're dealing with the 2s instead of the 1s, but the idea is the same. So I'll have my sigma and my sigma star for 2s. All right? Now dealing with the p's, things get a little bit more complicated. So my first level dealing with p orbitals is a pi. So I'm going to say pi 2p, and the pi has 2 slots. The next slot up is sigma 2p, and then the next slot up is my antibonding pi 2p. It also has 2 slots. And then at the very top, we have a sigma antibonding, sigma star 2p. That doesn't say 2p. And it has a single slot. Okay? And same deal here, this whole section goes with the p's. Okay? So, looks pretty intimidating, right? But it's really not. The only trick is remembering the order of how things are arranged in the P section, and we'll talk about that here in a second. But I have 10 electrons total to put in the center of my drawing. So I'm going to start at the bottom, and I'm going to fill from the bottom up using Hund's rule. Okay? So in my 2s, I've got 4 to play with, so I'm going to put my 4 electrons in there. So 1, 2, 3, 4. That takes care of all of my s electrons. Okay? Now in my p level, I have 6. Right? So I'm going to follow Hund's rule and the Pauli exclusion principle. So I go 1, 2. Notice I didn't put them both in the left hand, even though I could. I want you to pay attention to this. Fill them singly before you pair them. So I've got 6, 1, 2. Now I can pair them 3, 4, 5, 6. Okay? And the number of electrons in the center of the drawing should match the total number of electrons between the 2 atoms. Okay? So this is how we do an MO diagram for larger molecules with more valence electrons. Now let's take a look at the bond order just for fun, because I think you'll find it interesting. So the bond order is 1/2 the bonding minus the antibonding. So let's take a look. Our bonding orbitals are anything that doesn't have a star. So I've got 2, 4, 6, 8 bonding electrons, right? And then I'm going to change up the color just for fun. And then my antibonding is anything with a star, right there, right? My sigma star 2s is the only antibonding orbital that has electrons in it. So 8 minus 2, so 1/2 of 8 minus 2 equals 3. So guess what? Triple bond, right? And if we draw a Lewis structure for dinitrogen, guess what we get? We get a triple bond. Right? So when we're dealing with these larger molecules, there are 2 different arrangements of our Mo diagram. Okay, what we get is one arrangement for B2, C2, and N2. And we get a second arrangement for anything larger, so O2, F2, or Ne2. Okay, so let's take a look at what are the differences. Right, so if I draw, so we just did the one for N2, so I can go ahead and put that one down. So starting from the top, because it's easier that way to make sure everything is lined up. I had my sigma star 2p, and then I had my pi star 2p, and then I had my sigma 2p, my bonding, and then I had my pi 2p, and then below that was the sigma star 2s and my sigma 2s, right? Okay, now when we get up to the oxygen, what happens is that nitrogen, we have a half full p orbital, right? Which is very stable. And then when I get to oxygen, I've added one extra electron to that p orbital, and I've changed the energy of the p orbitals, okay? So that's going to affect the arrangement in my Mo diagram. So let me go ahead and just put this in here. So the sigma star 2p is in its normal place, as is the pi star 2p. But here's where it gets different. The next level down is now my bonding pi, followed by my bonding sigma. Okay, and then the S is the same. Right? Right, so where things get a little bit different, depending on what molecule you're making, is these places are flipped. Okay, and again, the reason for that is that your nitrogen 2p is half full, which is stable, right? Pretty low energy. And then when I get to the oxygen, when I go one more step up, the 2p has one more electron in it, right? Less stable, more energy. Okay, so that's why the Mo diagram flips. when you get above nitrogen. Okay, so you want to be aware of that when you're doing mastering and when you get to the exam. Okay, so let's do one more MO diagram before we call it a night. All right, let's do an MO diagram for something that's not homonuclear. Right, let's do a heteronuclear MO diagram. Let's do a diagram for NO. Okay, so I'm going to take and put my nitrogen on one side and my oxygen on the other, and I'm going to do my MO diagram to accommodate the oxygen, right? Because I just told you that they flip when you get high enough, right? So my 2p for the nitrogen is sitting there, and then my 2p for the oxygen is going to be slightly higher in energy because it's got more stuff in it. Right? And then we have down here our 2s, and probably about the same energy is the 2s for the oxygen. Right? So let's construct our diagram. So at the top here, I've got my sigma star 2p. The next one down is my pi star 2p, and then my bonding pi, and my bonding sigma. Okay. And then down here we have, of course, the antibonding 2s and our bonding 2s. All right, so let's put in our electrons for each side. Nitrogen's got 5 valence, so we're going to say 1, 2, 3, 4, 5. And our oxygen has 6, so let's put those here. All right, so now let's proceed to pack our electrons into the center of our drawing. So in the 2s level, I've got 4 electrons to add to the drawing. So I'm going to say filling from the bottom. There's 4. Now in my p level, I have 3 from the nitrogen and 1, 2, 3, 4 from the oxygen, so that's 7 total. So I'm going to fill from the bottom. So 1, 2, 3, 4, don't pair them yet, 5, 6, and then we move up to 7. Okay, so let's take a look at the bond order, because this will be interesting for you. Bond order, 1/2 the bonding, which we have 2, 4, 6, 8. Right? So 8 electrons in the bonding, minus the antibonding, which we've got 2. Then we come up here to the top. There's a third. So 1/2, 8 minus 3. 8 minus 3 is 5. So I've got a bonding order of 2.5. So what that tells us is that our bond is between double and triple. Right? So we've got some kind of like funny hybridization going on, or funny bonding. Okay? So it's an interesting thing. Now, here's the last thing that I want to talk to you about. Is this molecule paramagnetic, or is it diamagnetic? Okay, so remember, para is unpaired, right? So let's look in our MO diagram, and sure enough, I have an unpaired electron right there. Right? Everywhere else in this diagram, the electrons are paired up. Right? So is it paramagnetic? The answer is yes. Right? So NO is weakly susceptible to magnetic fields. Right? So let's come back up and take a look at one of our other MO diagrams and see if we can decide paramagnetic or diamagnetic. So let's look at dinitrogen. Right? Do we have any unpaired electrons? All of these electrons are paired up. So the answer would be that dinitrogen is diamagnetic. All paired. Okay, so that pretty much does it for us in this chapter. We've covered molecular geometries, we've covered valence bond theory, we've covered molecular orbital theory, and all kinds of wonderful things.